This is a continuation of section 10.6 and 10.7. I'm doing those together on parametric equations and their graphs. So let's go ahead and graph the set of parametric equations. Let's show the orientation and then convert it to rectangular form. Let's just dive right into using the calculator for this one, okay? So we're going to grab the calculator. We're going to make sure you're in parametric mode. So if you go to mode, you'll see that there's function, parametric, polar, and sequential. So you want to make sure you're in parametric mode. If you're not, use the arrow keys, go over to PAR and hit enter to highlight it. When you're in parametric mode, if you're graphing something that has like a sine or a cosine to it, some kind of trig, make sure you're in radian mode as well. So I'm just going to go ahead and put it in radian mode for this one. I don't need it in radian mode, but I just want it to be in there for later. So what that's going to do is, of course, this xt theta n button depends on the mode. If you're in function mode, it's an x. If you're in parametric, it's a t. In polar, it's a theta. And if you're in sequential, it's an n. So this button changes based on your mode. So if I go to y equals, you'll see that they're grouped, that x and y. So my parametric equations are the square root of t. And then my y is t squared minus 1. So I'm going to put that in and I'm going to hit graph. Alright, so it kind of happened, kind of quickly there. Did you see the orientation of what happened? If not, let's go to window. You can change the t-step. That's how quickly the t value changes. So that's going to tell you how quickly or how slowly it's going to graph. You don't want this to be too small of a number because it's going to graph insanely slow. So let's just, 0.1 was kind of quick, so let's just do like 0.08 and see what happens. So you saw that, how it started down here and kind of went up, right? So that was my orientation. So it was down here at -1, and then the orientation went up that way. Now this is for a t value from 0 to infinity. So let me go back to my window. I'm going to change that from 0 to infinity. Let's just put like a bunch of 9s in there and see if that, okay, yeah, that didn't change it. So why do you think we needed that 0 to infinity? Well, that's because that square root of t right there, right? That's that domain for the square root function. So we needed those values of t to be positive in order for us to be able to take the square root and get a real number solution, or a real number answer there. All right, so we got the graph, we got the orientation. Converting this to rectangular form, we're going to use a substitution. So if x is equal to the square root of t, then if I square both sides, I get x squared equals t. Now I did that because then I can substitute this value of t for this value of t. So I substitute that x squared in for t, and I get x squared squared, because that was a t squared, minus 1. So I get x to the 4th minus 1 is the rectangular form. Now this typically would look sort of parabolic. Not really, but I mean it would look sort of parabolic there. But it's only half of it because of that 0 to infinity. So it's only the right half of that thing. So if you were to graph this in function mode, you would get like that full kind of, U shape. But because of this, we only get that half of it. Okay, so let's do some more where we have to convert to rectangular form. So these, now you'll notice that sometimes I write x equals, sometimes I write x of t. It really does not matter. Sometimes I just drop that x of t notation because I'm just lazy. That's all. And I think it's just kind of cumbersome to write. That's all. So if I have these two, so these parametric equations for t not equal to 3. Now that's because obviously right here, if you have t is equal to 3, we get a domain error because we're dividing by 0. So how are we going to convert this to rectangular form? We don't have to graph it here. So you don't have to worry about grabbing the calculator. This one, if you look closely, we don't actually have to solve for t. Because this is t minus 3, and that's t minus 3, I can make a direct substitution. T minus 3 is the same thing, that's what equals means, same thing as x. So I'm going to replace that t minus 3 with x. So I get y equals 2 over x. Boom, done. If you did choose to solve this for t and you got x plus 3, and then you substitute x plus 3 in for t, you would get x plus 3 minus 3, and the 3's would zero off. You get the same answer. Okay, let's do this one because it's got some trig to it. Now this is for t on the interval from 0 to pi, non-inclusive. That is because the cotangent function is not defined on 0 or pi. All right, so how on earth are we going to do this? This one we don't try to do the substitution business. Don't try to solve this for t and then sub it in there. Instead, we're going to use a Pythagorean identity, and specifically the one that involves cotangent and cosecant. So 1 plus cotangent squared equals cosecant squared. So cotangent is t, cosecant is y, or sorry, cotangent t is x, and cosecant t is y. So substituting those in, we get 1 plus x squared equals y squared. Boom. That's it. I know it almost seems too easy. It seems like a trap or something. But no, if you know to use the Pythagorean identity for the trig ones, you're good. All right, so last one here. And this is going to go in the opposite direction. So rather than writing the parametric equations in rectangular form, we're going to convert from rectangular form to parametric form. That has a super sexy name. It's called the parameterize. So write the parametric equations for. So we've got this kind of super sexy name here that if you slap that down on a Scrabble board, you could just walk away like, just like, hey, you can't top that. So, all right, here's our rectangular equation. Now, I know what you're thinking. You're looking at it going, well, that looks just like the equation standard form of an ellipse, right? Right? That's what you're thinking? Well, it should be what you're thinking. So anyway, we're going to write the parametric equations for this. We're going to use x of t, remember that's the same thing as just x, is a cosine t, and y is b sine t. Okay. Now, we're going to make use of sine squared plus cosine squared is 1 because this part was given to me to use. So I know when it comes to, these kind of parametric equations, I am going to have to make use of a Pythagorean identity. Now, let's look back at example 2 that we did. Back in example 2, we had this rectangular form of x squared over 5 plus y squared over 3 equals 1. That came from the parametric equations of root 5 sine t and root 3 cosine t. Now, here's what this is telling us. So this is saying, hey, check out that x squared over 5. You see that? How it's, that's 5, but that was a square root of 5. That's 3, but that was a square root of 3. So that means if I were to have written this as x over root 5 all squared and y over root 3 all squared equals 1, then you can kind of more easily see how those are going to come about. So here's what I did. I took the original equation and I rewrote it as x over 3 all squared, y over 7 all squared. So if that's the case, then this is going to be my cosine, that's going to be my sine. Now, how did I know that? Because, well, it said to use sine for the y one, so the y one's my sine. So I get that x over 3 is my cosine, that y over 7 is my sine. And then just solving this for x, I multiply both sides by 3. Solving this one for y, I multiply both sides by 7. I don't know if it was really helpful to... Why is my chair squeaking like this? This is driving me crazy. And I'm sure you guys are probably thinking, what is that incessant squeak in the background? Anyway, we're almost done, so we're just going to power through the squeak. This example 2 business may not have been useful to you. It may have been more confusing. If so, pretend it never happened. All right. But I thought it might be helpful to just look back at the last time that we encountered one of these. We worked from the parametric equations to the rectangular form. That it might be helpful to you, but it might not be. So, in any case, the x one is the cosine, the y is the sine. Now, if you chose to write these backward, you kind of could, but because the directions asked us to write it, where x was the cosine and y was the sine, that's why I chose to use the sine for this one and the cosine for this one. And of course, if you put these parametric equations into your calculator, you would get an ellipse, which is exactly what that standard form would be. Okay, so that finishes up sections 10.6 and 10.7.